for chapter 6. Actually, I didn't publish it. I didn't upload. Okay. So the second part for solid solution, there's a calculation for it. We call it composition. Right? We call it composition. So the second part of this one, 4.2, is actually you are making alloy. You are mixing two different metals together. They will form metals. So there's a calculation for it. Okay, they call it concentration or composition. We measure by percentage. Right? There are two presentation. One is by mass percent. One is by atom percent. There are two presentation. So one is weight percent or WT percent or AT percent. WT means weight percent or mass percent. AT means atomic percentage. There are two presentation. So the trick of solving this kind of question, again, periodic table, all the element will have a small mass under there. So this is per mole. You need to change this one into all the answers. You change into 1 mole equal to how many gram? Right, 1 mole of that, how many gram? Or you're given like A 100 gram plus B 200 gram, then it become alloy. You go and find either in percentage, weight percentage, or atom percentage. Okay. Now the first calculation for second half, computation of weight percentage for 2 element. Later, if you have 3 element, 4 element, you apply the same, but I show you the 2 element. So first, because you're using weight, how you do for composition number 1, you take the total, take the ratio of number 1. Okay, so C1, concentration 1, this is WT percent. So means if you mix C1 plus C, you are mixing 1 element and 2 element together. You want to find what is C1 component inside the alloy. So what you do, you use the ratio M1 plus M2, you take M1 times 100%. Okay. So once you find the first one, let's say this one you get 80%. C2 automatic you can find. Why? Total is 100%. C2 will be 20%. Or 1 minus C1. Or 100 minus C1 or 1 minus C1. Because this one is 0.8 minus 100. This one is 1 minus 0.8, you get 0.2. Then multiply 100, you get 20%. Okay. So this is the first equation. So this one okay, for the mass, okay. What happened? You have the 3 element. 1, 2, 3. How? How to find concentration number 1? M1 plus M2 plus M3 M1 multiply 100. You want to find first concentration. Okay. C2, you cannot 1 minus C2. You have to also the same. M2, sum of OM multiply 100. Same. Okay. Second method is atom percentage. Atom percentage is you are using mole already. Number of mole related to total mole. This one is the one you learn in your chemistry. Okay. So for example, number of mole, you need to calculate number of mole first. So number of mole is atomic weight, you take it divided by the mass. Okay, so again, this one for atomic percent, 80%, you read from the periodic table, you take the gram over here, then you're given, for example, copper 100 gram. The N, 1 for copper is 100 divided by the Avogadro, the mole over here. Okay, so here you get number of mole. Okay. So percentage of 80% atom percent, you're looking at ratio of mole. So let's say you have 2 elements. So you take the total mole divided by the element there. Yeah. So the presentation here, if the question asks you atom percentage, please use C, comma. If the question asks you weight percentage, please use C without the comma. Okay. Make sense, Okay. So C1 and C2 again, percentage will be 100%. So if you only have 2 elements, you only need to find one of it, then 1 minus the 100 minus the C1 or C2. Okay. Again, if you have more than 2, you need to do the same. If more than 2, the below one is N1, N2, N3. Then you find the one that is missing here. Yeah? Okay, make sense, Make sense, Yeah, make sense, Okay. Now, so you want to do conversion. You want to do conversion. So we have 2 types, WT and AT. Sometimes question give you AT. You need to convert AT back to WT to calculate. Sometimes question give you straight away give you WT. You need to convert back to AT to calculate how many mole of that material you need to pour inside the solution. Okay, so there's a conversion there. So this conversion again, I need to stress, is for the 2 element only. You cannot do more than 2, this formula. More than 2, you need to do separately, this one. So if you want to convert WT or weight percentage back to atomic, you use this formula. So C1A2 plus C2A1 divided by C1A2 to do conversion. Same with this side. You only need to do 1, then this side is 1 minus this side, or 100 minus this side. It's the same. You should have 100%. Okay. I won't go through the derivation steps. So it is a quite lengthy process. So the same. If you are given atomic percentage, then you convert back, right? Right. Now the concept is the same. The derivation step is using convert from mass into mole. Then from mole back to mass. It's the same. Okay. Okay, so this is very convenient. If you can memorize, then memorize. Cannot memorize, you do the slow one. You convert from 1 by 1, then go back to mass. Okay. Okay, so this is derivation. I show you once how you do it. So let's say you have 2 elements for the alloy. So M1, M2, let's say. So you have a total mass M, comma, small m1, small m2. So again, you can straight away calculate by atomic percentage, okay, by converting the how many mole you have for each component. Okay. So number of mole, you take the mass divided by the atomic weight. Okay. So here, you take the Nm, change to M1 divided by Na. You take like this one. You can do the rearrangement, right? How to combine these two? This one multiply by A2. This one multiply by A1, so that you get the same denominator. Okay, once you get the same denominator, you can flip up. Then you combine the numbers. Make sense, huh? It's just a rearrange of your equation. Sense, huh? Okay. So you slowly, you rearrange, you'll get your C1 of that lah. Okay. So this one is another one, right? So you divide by 100 lah. Okay. So this one, if your C1 is M1 divided by M2 times 100. So you rearrange equivalent to the formula. Then you get another one lah. Okay. This is just a simple derivation steps. But again, I would highly recommend you go to the very traditional way. You convert what you have into what the question wants. For example, if the question wants you to do in mole, you convert the one that you see in the question into mole first, then you do the ratio. Okay, the calculation for this one, very easy. The bottom one is total you have, the top one is your target. If the alloy one, that you put alloy one, oh, this one is the total inside the solution. Okay. Okay, give you another example. Determine composition of atoms of alloy consists of aluminum and copper. You're given 97% and 3% of copper. So if you see this one, straight away go to the periodic table. Okay, you're given mass percentage, you need to convert to atom percentage. So what you do, you go to percentage, so 97.3. So you can either memorize the conversion, or you slowly do the calculation. 97% of W weight aluminium and 3% of copper. I'm showing you the one on the whiteboard. Slow way, or you can memorize. Slow way. The next steps, once you write this one, you need to act clever. How to act clever? Assume you have 100 grams. Or you can 1 kilo also can if you want. But normally I recommend 100 grams. In 100 grams, how many grams you have if you have 97%? So this one, aluminium, you have 100 grams times 97%, you have 97 grams. This one, copper, in 100 grams, you have 3 grams. Then go to periodic table. What is the A for Al? You go and find how many grams per mole. Same with copper, how many grams per mole? This one refer to table. Okay. Then how many mole? How many mole of aluminium when you have 97 grams? So you take 97 divided by this number. Okay, this one is from periodic table, aluminium. Same with copper. 3 divided by periodic table value, copper. So you have a ratio, right? How many mole? How many mole? So let's say I put A, this is B. So 80% of aluminium equal total how many mole? A plus B divided by A times 100, you get 1. Same here, B divided by A plus B, you get how many percent? But this one is in 80 atomic percentage. This slow way, or you can memorize this one. But I would highly recommend you go traditional way. Okay, so this one you plug in, you'll find 98.7%, 80. For copper, straight away, take 100% minus this number, you get for copper. Okay, or you can calculate also lah, if you want. Okay, so we are done with the concentration conversion. Also very popular when it comes to final exam and also test 2 question. All right. Okay, now we start to, once you're done with the concentration already, we go into the defect inside the alloy. Defect, or what are the terms that we use? So for solid solution means is in the solid that you make, it consists of 2 or more elements in the structure. So there are 2 solid solution, means that you want to make the metal stronger. How you make the metal stronger? You have 2 ways. Either you do substitution or you do interstitial. What I mean by substitution means you take out the molecule, substitute with another one. This one, the rules must be the radius that you use for substitution must same as the holes. When you substitute, the radius must not create stress to surrounding atoms. Okay, so the radius must be very, very near to the surrounding. It can be smaller or can be bigger a little bit only, but cannot be too big. Too big, it become another problem already. Another one is called interstitial. Interstitial, like you're putting a spy inside the space there. You put in one, not substitute, but you put in additional atom inside there. This is called interstitial or impurities atoms. There are 2 ways of making solid solution or strengthening metals. There are 2 ways. One is substitutional, one is interstitial. There are 2 ways. If you're using substitutional, the size of the molecule or the substitutional atoms must be similar to the host. If you are using interstitial, you must be carefully calculating the space that you have within the atoms. So for example, chapter 2 application. Okay, I use the BCC. Right, BCC center and then the 4 corner, right? So if you want to do interstitial, what do? You need to calculate the space that you have here. You know how to calculate, right? These are. The maximum space is here. The maximum diameter that you can put in is 2R for BCC. Make sense, huh? Understand, right? So this is BCC. Okay. Okay, so the one they see on the screen here is substitutional, means you substitute the solute items and parents solvent. Okay, 2 keywords here normally will be confused by the class, and usually in the exam you're confused. One technical word called solute atom and solvent atoms. Solvent is the host or the original solid, original liquid is called solvent. Okay. Usually question will ask you solute atoms, where you pour inside or you put inside there. Yeah, don't confuse within solvent and solute. Okay. Solvent, a solute is the one that you put inside. Solute. Okay. Okay. So the fraction of atoms of one element that can dissolve in another one, you are using fraction of atomic percentage. There lah. Okay. So we are using how you know that you can put inside additional there by two methods, substitution and interstitial. There are two methods by using Ohm's rules, HUME, or HR rules, Ohm's rules. So if the question forces you to use this one, you need to write what is the condition for these rules. There are three rules. Under Ohm's rules, or the question can ask you in section 1, explain what is Ohm's rules. So these are the 3 points that are expected from your answer. What is HR rules? Diameter of atoms cannot be differ more than 15%. Means the diameter of the atoms cannot be bigger or smaller than 15%. Okay. This one is for dissolve. Dissolve in another one. So one is diameter, cannot more than 15%. Crystal structures of two elements must be same. That's why I ask you to remember three members from BCC, FCC, and HCP. Only the same crystal structure can join. You cannot take BCC, join FCC, can, but you're creating another problem. Yeah. Crystal structure, the third one, it should be no appreciable difference in electronegativity. Electronegativity, this one is for the chemical reaction. This one, electronegativity. So how you know the electronegativity? In the periodic table. So this is 1 and 2. This one is of 6 and 7, 8 here. Okay. So when we do substitution or when we use HR rules or Ohm rules, we rarely take group 1 join with group 7 because you have a chemical reaction there. We don't want to have this one. We only want to stabilize the things. Normally they are quite near. For example, their own family lah, or here own family. Okay. So electronegativity also linked with the SPDS that you write on the periodic table because of the energy. If the energy is quite close, so you're still safe. If the energy is quite far, then there's a reaction there lah. So three criteria for Ohm's rules. Diameter must be the same, almost same, about 50%, 1.5. Crystal structure must be the same. What are the crystal structure? The three already learned, BCC, FCC, and HCP. And electronegativity must be almost same lah, almost same. Number four is linked with number 3 point, is they have the same valence. What I mean by same valence? Same family lah. Valence means the outside electron have the same. Like for example, family 1 all have 1 electron outside. Family 2 have all 2 electron outside. So they have the same like energy like that. Okay. Okay. So we don't want to have shortage of electron because the binding will form. You learn about the covalent bond, triple bond, single bond, and all this. So we don't want that to form during the mixing. Okay. So again, you learn about HR rules. Okay, then we look into interstitial. Okay, the previous one, HR rules, this one is more on the substitutional rules. Okay, this one, HR rules is more on the substitutional. Then interstitial means you fit inside alien atoms in the solvent. You put solute atom inside solvent, like the one you see on here. Ion radius is 0.129 nanometer, and the carbon is smaller than the atom, 0.075. So it can fit inside the space between the ion. Okay. So interstitial, the keyword there is space. Which one? This one. It's a stretch or something lah. Okay. But anyway, okay. One thing that you learn in chapter 2 is called coordinate number. Coordinate number 8, it means we got eight atoms surrounding it, the atoms. Okay. Okay. All right. Another one is called, if you have a cube side, it means the coordination number is 8, octahedral is 6, tetrahedral is 4. The coordinate number, coordinate number means 4 atoms connect to that atoms. Octa 6, cubic is 8. Okay. So solid atoms must always be larger than the radius of interstitial void. So it creates a distortion to the lattice. So smaller, like hydrogen, carbon, nitron, and so on. Okay. So this one, the last statement here, we will learn when we go into phase diagram. So I just conserve this one first. Okay. So here, if you compare carbon and ion, or this diagram, the radius difference is 42%. Okay. So under experiment, they found out that maximum is 2% of the carbon can dissolve in the space between the ion. Okay. Now, example 3. We go through example 3, then maybe we stop here, then we continue 4 o'clock. Right. Now, calculate the radius of largest interstitial void in FCC gamma ion. The atomic radius of ion is 0.1 nanometer in FCC lattice. Largest interstitial void occurred at, again, these are the position, right? Previously, we learned about position, vector, direction, family, and so on. So it appeared at half, 0, 0, 0, half, 0, 0, 0, half type of position. So it's a half family. Also identify the classification of the given interstitial site. So like this kind of question, you always start with a diagram. Okay. So FCC, you draw FCC lattice. Then if you are showing 1, 0, 0 position plane, 1, 0, 0, you should already know how to draw the plane. 1, 0, 0 is the one that you see on here. Okay. So if you have FCC, you know FCC, right? FCC, you should be seeing something like that, right? So you have 1 in the center, 4 at the corner. So let the radius of item be the R. that the interstitial void position 0, 1, 0 be the R. Okay, means at the center of here. Okay, so you draw the FCC. So this is a four corner atoms. So this is the metals ion R. This is R. This is a space that you can fit in atoms, additional atoms. So let's say this is a 2R, 2 small r. This is big R that you have. So you know that this is your Rubik, your cube. This is your A that you learn in your chapter 2. Your A will equal to 2R plus 2 small r. Make sense? Makes sense, right? Okay. Okay, that makes sense, huh? Who don't understand why suddenly 2R plus 2 small r equal to A? This is FCC, so you should be seeing this one. So FCC, four corner, you have one atom here, one atom here, and this is the additional alien that you can, the space that you can form. So this small one is 2R. This one is R, this is R. So you have two big capital R and two small r. Equal to A. A is the cube side. Okay. Then you try to relate what is your R and small a. You need to do the calculation again with the R and A. So what you do is that you draw a right angle triangular here. So here to here is R plus half R. Here to here, big R and small r. This one half ma. Okay. Okay. So then this one is a half A. This here to here is A. Here to here is half A. Here to here is 2R. This is the original host. So R and R. So you have 2R and half A, half A. So you write into Cartesian plane, 2R square equal to half square A plus here. So when you do the calculation, you get half. So solving for A, you put your square here, you square root this one, you get half over square root of 2A. Or your A equal to 2 square root of 2R. Okay, so in fact, you're seeing this one in chapter 2 already. Next, you further arrange the equation. Just now, you link with the alien atoms, 2R plus 2 small r equal to A, equal to 2 square root of 2R. Then your R will be 0.414R. What does it mean? This small alien atom radius can only be 41% of your host radius. Make sense, huh? And this kind of question will continue. Suggest the possible atoms that you can use for this alloy. Not periodic table. There's a table. There's a table that you see very frequent in chapter 2. You will see material. You will see A. You will see R. You will see other things. So let's say this one is tell you that the alien atoms you already calculated already. You can maximum is 41% of the host. Here you can calculate, right? For example, this is ion Fe. You have one value here or one value here. This is also same. A and R is the same, right? So now you're looking at the R this side. So you're finding the size must be 41% of the R. So you find which one is 41% and below. You understand or not?
1% of the original.
Yes.
Bigger or not.
It cannot be bigger because this is the size that it can fit in of the host, of the R of the radius So from the table you find
So it's not saying that the replacement cannot surpass 41 or not smaller than 41.
No, this is not substitution. This is you inject an alien atom inside there. It's not replaced. This is not HR rules. This is interstitial. There are two types of method of strengthening metals. One is substitute. Substitute, you pull in this one out. That one you use HR rules. Cannot more than 15%. The difference cannot more than 15%. But this one is interstitial. You need to use the calculation like what you see on this example. Find the ratio of the small r and big R. Then you go back to the table. You find which one is less than 41%. Okay. So in this case, the FCC in the table is 0.21 nanometer, or it's given in this case. So the R will be 0.514 nanometer. You use this value, go to the table and find which one is smaller than this one. Make sense, huh? Okay. Okay. So like the one I draw on the canvas here, I draw the blue dot, green block, green dot there. Okay. So you can have how many green dot in this FCC cubic? How many you can fit the green dot? One here, one here, one here, one here, 4. Top 8, right? Here you cannot what? Here too small what? Here already like squeeze the space already, cannot. All right. So given the void have 4 neighbors at the plane, one neighbor directly above and one neighbor directly below. It is here and here. Right. So the total neighbors or coordinate numbers is 6. Can you imagine? The solute atoms. This one, the green color, you have coordinate number of 6. Can you imagine 6 members around the green ball? You are the green ball. You are the green ball. How many atoms or how many spheres that you are touching? 6, right? So coordinate number is 6. You are the green ball. You are touching 6 spheres. 1 at the top, 1 below, 4 around you. Right? Okay. So this interstitial void classified as octahedral. Once you find the value R, you draw inside the crystal structure. Then you imagine how many atoms is touching. Then from there, you classify as one of the octahedral. So try to memorize this one. This one, If you have coordinate number 8, it's a cubic. If you're octahedral, you have 6. If your coordinate number, you have 6, it means you fit inside there, then you imagine how many atoms you're touching. If it's 6, then it's octahedral. If it's touching 8, then it's cubic. If it's touching 4, then it's tetrahedral. There are 3 names that you need to memorize: tetrahedral, octahedral, and cubic from the coordinate number. Okay. Okay, we stop at this example. This afternoon, we continue. Wait, Okay. Okay, this one maybe we continue next week. This afternoon we do revision.